All right, so now we're in chapter 16, our last chapter, and this chapter is all about chemical equilibrium. So we're going to start by talking about something that we've considered, an equation that we may have seen in the past, same type of chemical equations we've been looking at all year long. But I need to go ahead and apologize to you guys. Because for an entire year, this is the way that you thought chemical equations worked, right? This is kind of normal, and you're used to it, you're comfortable with this now at this point. But I'm about to rock your world. Are you guys ready?
No.
Here we go. What? Right? Are you kidding me? What is that? So, as it turns out, chemical equations can go this way. But as the products are being made in the original reaction that I put up there, as those products are made, if there's enough activation energy, enough energy to start the process, these guys can start reacting with one another and start making the reactants again. So actually the equation can go back and forth. The reaction can happen in both directions. All right? Again, if there's enough activation energy for that to take place. So that's why we have to talk about this idea of chemical equilibrium, because if it can go in both directions, does it just, what is it, it's like swinging this way and then swinging back this way? Well, that's not how these types of reactions work. What actually ends up happening is, if it's a reaction that can kind of go back and forth like that, is eventually it settles down and you reach a point where you basically have the same concentration of all of these products that levels off and it doesn't change. And when we hit that point, we call that chemical equilibrium. All right, so let me give you a definition of that. It's basically the reaction rate, right? We've got this happens at a particular rate as we move forward, and then as this one begins to happen moving in the other direction, that happens at a particular rate. And when those rates equal one another, we say we're at chemical equilibrium. So chemical equilibrium is the state that occurs in a chemical reaction when the rate of forward reaction, right, the one that we've solely looked at all year long, the rate of the forward reaction equals the rate of the reverse reaction. Right, so you kind of get, if we were to graph that, and we put our reaction rate over here on the y-axis, and this is time down here on our x-axis. When this thing first starts, we've got only products, and we have a curve that kind of looks like that. And as those products are being made, though, this is only reactants, Reactants is all we have at the top. They begin to react, but as it makes products, then the products start to react. So this is our forward reaction right here. And once it begins to make products, then you can start having the reverse reaction. But at some point, the reaction rate of both will equal one another, and that's the state of chemical equilibrium. All right, so you guys understand the concept, right? You get what's happening? Now, we haven't been dishonest all year long. It's just that we've looked primarily at reactions throughout the year that have been heavily weighted in the forward direction. And so you get way more product than you do reactants. And so in that case, it's appropriate to just think about that as having the arrow in one direction. So we're going to talk about how we determine when you should just write it like this versus when you need to write it with both arrows to show that it happens in both directions. Okay. Now, as an option for you, as we're getting near the end of the year, give you an extra credit opportunity. Experiment 16.1 can be done for extra credit. And so I'll put an assignment out there for you to do that. It's a pretty simple experiment. You don't need a whole lot. Pretty easy to do at home. But I need a pic. So upload to Google Classroom a pic of you doing the experiment and the lab report. Okay? So both of those. I want to make sure you actually do the experiment and not just simply write a lab report for me. Not that anybody here would do that, right? But some of our other classes, they're not as trustworthy as you guys. All right, but there's an extra credit opportunity, and I'll just, I think I've said this to you guys before. When we have extra credit labs, a lot of times that'll raise your overall semester grade like a whole point. So it's kind of a significant increase in your grade. That's pretty good extra credit. So these things will go back and forth, and at the point at which we reach chemical equilibrium, we in essence think of the reaction as having stopped. Even though it's still making products and it's still making reactants, it's just everything levels out, and you're making products at the same rate that you're making reactants, and so there's not really any change in the chemical equation at that point, and we say that the reaction's effectively stopped. Now, what we calculate for these chemical equilibrium reactions is something called the equilibrium constant. And so this is where the math comes in, right? We've always got to have some math problem in chemistry. And so basically we use a capital K to represent the equilibrium constant. And it's going to be based on the concentration of the substances that are in the chemical reaction. So basically, if we have a reaction that we define as little a, big A, plus little b, big B, yields little c, big C, plus little d, big D, where the little values in front here are just the stoichiometric coefficients in our equation. So if we had a 2, for example, in front of this these two values here, then this would be like big A would be CO2 and little a would be the 2 in front of it. Okay? I'm sorry, not big A. This is the reactant side here. Big A would be CO and then have a 1 for little a. Big B would be NO2 and then have a 2 for little b. Does that make sense? All right? So if you think about it like that, then we can say K is equal to the concentration of big C raised to the power of little c, and this is the concentration at equilibrium. So we use these square brackets here to mean concentration, all right? Times the concentration of big D raised to little d, and that's the concentration at equilibrium. So we write little eq down there. Divided by the concentration of A at equilibrium raised to the power of little a times the concentration of B at equilibrium raised to the power of little b. All right, so this is right here is the concentration at equilibrium. So it gives us a way to numerically represent that state of equilibrium for a particular reaction. So the easiest way to understand this is really to just do an example. So if we go to page 487, we're told that we're given a reaction here, and we're told that the reaction is 2NO as a gas plus 2H2 as a gas. They write the arrows back and forth so we know it's an equilibrium reaction. And we have N2 as a gas plus 2H2O as a gas. All right? And they tell us when this reaction starts that the concentration of both NO and H2 is 0.1 molar. Right, we had 2 units that we used for concentration. What 2 units did we use for concentration? Do y'all remember? Molarity was one of them, and molality was the other, right? So the capital M, we're familiar with that, using that as a unit of concentration. So that was the concentration when it starts, and these guys are both at 0 M when the reaction starts. It just means, to start with, we only had these guys, and we didn't have any of this stuff, right? And when we hit equilibrium, it says that the concentration of NO and H2 are 0.024 M. So I'm going to write this like this. The concentration of NO at equilibrium, right, using the symbols that we just learned, they tell us that that is 0.024 M. That's our unit. The concentration of H2 at equilibrium is also 0.024. And then the concentration of the concentration of N2 is 0.038 at equilibrium. Was it 3.8? Is that what I said? 3.8 and 7.6, yeah. So 3.8. And then the concentration of this guy, H2O, is at equilibrium is 0.076. All right? And what they ask us to do for this bigger problem is determine the equilibrium constant for this reaction. All right? So we're just going to use our formula over here. Let's plug this formula in and make sure that we understand that. All right? I didn't mean to go up so high. Just leave down here. There we go. All right, so K is equal to, for our equation, what part corresponds to the concentration of C, big C? N2. N2, right? Good. The concentration of, let's put Josh up there. The concentration of N2 at equilibrium. And what's the little c power that it's raised to? 1, right? There's an understood 1 in front of this n right here. We could write it in there if you wanted to. So that one's just going to be raised to the power of 1, right? And then next we've got the concentration of H2O at equilibrium. And that one's raised to a power of 2, because that's the stoichiometric coefficient on that guy, right? And on the bottom here, for A is NO, right? So we have the concentration of NO at equilibrium, raised to the 2nd power, and then the concentration of H2 at equilibrium, also raised to the 2nd power. Does that make sense to everybody? Okay? So let's just plug those values in. Concentration of N2 at equilibrium is 0.038 molarity. It's raised to the power of 1, so we won't put a power on there. H2O is 0.076 molarity, raised to the 2nd power. Concentration of NO is 0.024 molarity, raised to the 2nd power, and then H2 is also 0.024 molarity, raised to the 2nd power. Bless you. Now, we've only used these values down here. What about these concentrations that they gave us up top when the reaction started? Where do they figure in to the equilibrium constant? They don't, right? That was just extraneous information that they gave us to make sure we knew what we were doing. They don't matter because we only care about the equilibrium, the concentration at equilibrium when we're figuring out the equilibrium constant, okay? So don't let those values throw you off. I think I gotta use those somewhere. So this is what we're punching in our calculator right here, and we come up with a value of 660. Sorry, I wrote an O in the middle, a 0 in the middle in there, and that's why that 6 looks so strange. I turned my O into a 6 in the middle. And what's our unit for this? Does everybody see that as far as the units would go, we would have m cubed on the top, and we would have m to the 4th on the bottom. So our final value is actually 661 over 10. That's actually our answer. And so I just say that to make you aware of the fact that when we stick our molarity units in there, depending on the power that these guys are raised to, which is based on the coefficients, right? That unit's not going to always be the same. So you're going to have to do the little algebra canceling out to figure out what the final unit's going to be. It could be 1 over m, could be m squared. It just all depends on those coefficients and what powers these values are raised to. All right? Does that make sense? You guys good with that? Now that you've done it, it's pretty easy, right? Not hard. So, one thing to note is that the value of K, the concentration of these guys at equilibrium, will change with temperature. And so sometimes they didn't, because they hadn't told us that yet, they didn't include the temperature in this reaction, I don't think. Let's see. They didn't say anything about temperature, did they? On page 487. Yeah, they didn't mention the temperature. But the next example that we do, they're going to tell us that, actually they don't mention it there either. We're going to see some though in the future where they say, this is the equilibrium values at this particular temperature, and the temperature doesn't figure into anything. They're just making sure that you know these values are only valid at this temperature. Because if we were at a different temperature, the equilibrium concentrations would be different. So that affects it. Just something to be aware of. More importantly, I want to make sure that you guys understand this. When you're calculating the equilibrium constant, if K is large, there are more products than reactants. At equilibrium. And what we say is that reaction is weighted towards the products. If K is large. And we'll talk in a minute what we mean by large. If K is small, the reverse is true. If K is small, more reactants than products. In other words, the reaction is weighted towards reactants. And finally, if K equals 0, if K equals 1, reaction is balanced between the two. All right? So you can memorize these, or you can kind of think about the equilibrium constant equation. And if you think about that, which part of this fraction here, in our equilibrium constant equation, which part of this fraction would have to be biggest in order for K to be large? The top or the bottom? The numerator or the denominator?
Numerator.
The numerator does, right? Does everybody see the bigger this number gets here, the bigger K gets, right? Like if you have a fraction, if you have this fraction 3/4, and you make the top number, if the top number is getting bigger, so now you have 6/4, and then you have 8/4, right? The overall value of the fraction is getting larger every time I do that, right? And what is in the numerator of the equilibrium constant equation? It's the products, right? So if you think about that, then it'll make sense that if K is large, we've got to have more products than reactants, right? The product number is big and the concentration of the reactant is small. But if that's being flipped around and our numerator is bigger than our denominator is bigger than our numerator, in other words, the concentration of the reactants is greater than the concentration of our products, then K would have to be small because we've got a bigger number on the bottom than the number on the top, all right? Yep.
Okay, so just for clarification, even though the reactant thing goes both ways, still the left side is the reactants and the right is always the product, no matter what. Yeah.
Yeah.
I was afraid of that answer.
Yes. So if this is heavily weighted towards the products, all right, if K is really large, then we don't write 2. We just write 1 arrow in our reaction. Okay? If K is what we consider to be really, really small, and we have this case here, we write the arrow. We could write the arrow that way. We'll talk. We don't usually do that. Usually we just flip the whole thing around, and what was the products becomes the reactants. Okay. All right. So you're asking a good question, right? This is part of what we have to figure out. But when it's 1 or near 1, that's when we're going to use this to represent our reaction. Okay. And so what value do we consider to be large enough to where we would write just this? Okay. I mean, your question was a perfect segue into the next point. If K is greater than 1 times 10 to the 6th, all right, that's when we say it's large enough that it's so heavily weighted towards the products that we would just write an arrow in one of this direction. Okay. If K is greater than that, arrow is that. All right. Conversely, if K is less than 1 times 10 to the negative 6, then we say the arrow it's so heavily weighted towards the reactants that we would write it like with the arrow pointing towards the reactants. Okay? That's 2 separate words. It looks like I came up with a new word called arrowis. Arrow is. All right. And so this last K, of course, is just K anywhere between those values, right? Every other K. Arrows are that, right? So it doesn't have to be exactly 1, it just has to be within this range here. And so if I give you a problem and I ask you to write the arrow in one way or the other, this could be something like, instead of being 1, maybe it's 330, right? Or it's negative 96, right? It's just somewhere between these values here. But if you calculate K and K turns out to be 4 times 10 to the 20th power, right? Then we're going to just write the arrow pointing that way. If it's 6.2 times 10 to the negative 8, we're going to write the arrow pointing in the direction of the reactants. All right, does that make sense? Good question. That's worth your name being on the board, right? It's like I slipped her a 20 and said, okay, ask this question at this point. So it just flows really well into what I'm telling you. All right, so let's talk about, actually they have another example for us to do. Example 16.2, page 489. And so they ask us here in this case, how could this reaction be written as a one-way reaction? And they tell us, for this particular problem, I'm going to erase this here. They tell us for this problem, they give us a value of K as what? What's K? K equals 1.4 times 10 to the negative 25. Oh, they actually do give us a temperature, right? So I was thinking they did. They tell us it's at 25 degrees. Again, that doesn't have any bearing really on how we think about the problem. It's just because the equilibrium constant will change depending on the temperature. And so they say, if I've got this as my reaction, 2SO3, and on my reactant side, and 2SO2 and O2, 2SO2 plus O2, how would I write the arrows here, given this value of K? Which way should the arrow go? Which way? That way? Yes. So it goes, it's weighted towards the reactants. Does everybody see that? Because K is really, really small, right? It's less than 1 times 10 to the negative 6. And so this is why I was saying, based on your question, Annalie, you never see a reaction written this way, right? If it's a reaction that's heavily weighted towards the reactants, then we would just turn the thing around and we would write it like this. Right? But if I give it to you on a problem, you're going to be drawing your arrow that way to show me it's weighted towards the reactants. Okay? All right, any questions about that? Now, when we talk about calculating K, it has to do with concentration, right? The K equation, the equilibrium constant equation, is based on the concentration of the products and the concentration of the products and the reactants. And so the concentration of a solid is only determined by its density. And what happens with a solid is as it's used up, and the density is the number of grams of that solid per unit volume. As the solid disappears in a reaction, its volume goes down as well. All right? That's not necessarily the case for a gas, because the gas is kind of floating around, and it doesn't necessarily have to change volume the way that a solid would have to as the solid begins to be used up and disappearing. And that actually is true for a liquid as well. As the liquid is used up, then the volume goes down as well. And so one of the things that we need to remember is do not use solids and liquids when calculating K. All right, so you can just ignore those. If you've got solids and liquids in your equation, they do not affect the equilibrium constant. But now, do use gases and aqueous solutions. All right, you may think, well, aqueous is basically a liquid, but remember, it's an amount of substance in a certain amount of water. And so the concentration for that can change, and it does affect the K. So do not use gases and do use gases in aqueous solutions when calculating K. And so, as you might expect, they give us a reaction here and say, hey, tell me what the this is 491. Tell me what the equilibrium constant would be for a reaction that was CaCO3, solid CaO as a solid and CO2 as a gas. So they ask us to just write the formula for K for this guy. All right? And so what I would encourage you to do is, if you see an equation like this and you're having to calculate K, I would just go ahead and put a slash through any solids and liquids so that you don't accidentally forget what you're doing in the middle of trying to figure it out, and accidentally include those. Because like the next example we're going to have, there's 1, 2, 3, 4, 5 different substances in there, and it would be easy to overlook one if you don't just right from the start cross them out, right? So remember, K is the concentration of the products raised to the power of the stoichiometric coefficient divided by the concentration of the reactants. And so for this one here, the only thing we have is the equilibrium of the product, which is on the top of our equation. It's raised to the power of 1. So that right there would be the equation for this reaction, the equation for the equilibrium constant for this reaction. That's all we would include. Does that make sense to everybody? Okay? So in other words, they could give you just the concentration of this at equilibrium and not even tell you anything about these guys, and you would automatically know what K is because it's equal to the concentration of that at equilibrium, since that's the only thing that you figure into it. Does that make sense to everybody? I don't think there's any need to go through the next example if that's clear. The next example, they've got 5 substances in the reaction. One of those is a liquid, so you ignore the H2O at the beginning. This is at the top of page 492. And so all that's on top of our K is just HNO2 raised to the 3rd power, that concentration. And then on the bottom, you've got the concentration of NO squared, the concentration of NO3, and the concentration of H+. Right? Yeah. Those are the substances that are gases in aqueous solutions. Yes?
Why is H+ on the bottom?
Because it's a reactant. It's to the left. All those first 4 substances are all to the left of the arrows. You see it? Yeah. Okay. So yeah, that's a good question. You know, the number of substances are going to vary depending on how many products and how many reactants there are. All right. Okay. Sometimes we'll be given a reaction, and we'll take a sample to figure out the concentration of the various substances in the reaction at a particular point in time. All right. And then we're asked the question, is this reaction at equilibrium? And so in order for us to figure that out, we're going to have to know what the value of K should be at equilibrium. All right? And so that's what this next example is about. They give us a value of K, and they tell us what the concentration is of the substances at a point in time, and they say, is this reaction at equilibrium? And if it's not, which way is the reaction going to shift? Is it going to shift towards the products or shift towards the reactants in order to reach equilibrium? Okay? So let's do that one. This is 16.4. And they tell us that K is 4 times 10 to the negative 6. All right? Molarity. That's what it should be if the reaction is at equilibrium when we calculate K. But at a point in time, at the temperature of 1100 K, again, that doesn't figure in our calculations at all. Let me write this down. 2H2S as a gas. 2H2 and S2. 2H2 as a gas, S2 as a gas. At a point in time, they determined that the concentration of H2S is 0.01. The concentration of H2 is 0.000222, and the concentration of S2 is similar 0.00011. And all of these are molar values. So just a capital M is our unit on the end. And they say, at this point in time, is the reaction at equilibrium? Now, why did I not write EQ next to each of these concentrations right here as I listed them?
No.
We don't know, right? We don't know if we're at equilibrium yet. We got to calculate what K would be at this point in time and see if it matches this, all right? So, what we're going to do is we're going to take the concentration of the products, 0.00022, right? Raised to what power? What's that going to be raised to?
2.
2, right? It's got a 2 in front here, times this concentration of S2. There's no coefficient, there's an understood 1 in front of that, so we're just raising it to the power of 1, divided by 0.01 molar, which is also raised to the power of 2, because that's our coefficient right here, right? And so we do the math for that, and we get a value of 5.3 times 10 to the negative 8 molar. That's what we calculate K to be. Is it at equilibrium? It's not, right? Because this is not the same as that. So not at equilibrium. Does this number here need to get bigger or smaller to be this number? It needs to get bigger, right? This number is smaller. It's 10 to the negative 8, so it's smaller than this 10 to the negative 6 number. And so if it's got to get, so needs to get bigger. So reaction will shift towards, if it needs to get bigger, do we need the top or the bottom of our fraction to get larger? If K needs to get bigger, does the numerator or the denominator need to get larger? The numerator, right? The top part. The top part is the products, so this guy's going to shift towards the products. Needs to get bigger, so reaction will shift towards products. Any questions about that? Does that make sense to everyone? So we can kind of summarize what we just said as far as that goes like this. If no K and take concentrations at a point in time and calculate K at that time, then if the value that we calculate equals K, reaction is at equilibrium. If the value we calculate is less than K, then we'll shift towards products. And if the value that we calculate is greater than K, we'll shift towards reactants. So again, if you can just remember that idea, top part's got to get bigger for the number to get bigger, and you don't even really have to memorize that stuff, but you will have questions like this, and you'll need to be able to tell me which way it's going to shift. All right? Any questions up to this point? You guys are getting your money's worth today. We're cruising at lightning speed. So yes.
I feel like I want to buy a Pop-Tart.
You want to buy a Pop-Tart? Is this too much? It's like you need some more energy?
I didn't eat breakfast.
Yeah, you're going to get one. I'm going to talk about Le Chatillier's principle while she's running to get her Pop-Tart. I'm going to introduce you to Le Chatillier's principle. All right, so let me write that down. That's a weird name. Weird sounding name. French guy. So Le Chatillier's principle deals with a scenario like this. So let's say we have this equation here, N2 as a gas, plus 3H2 as a gas, equilibrium reaction, 2NH3 as a gas. And we're going to write down the graph of this initially. All right, so this reaction starts, we don't have any product and we've got only reactants. And so it starts, and here's our reaction rate. Like that first graph we wrote on the board. Here's our time in seconds. And we say 20, 40, 60, 80, 100. So 20 seconds, 40 seconds, 60 seconds, 80 seconds, 100 seconds. Basically right here, looks like this, looks like that. Can't believe I didn't connect that. Let's try that again. There we go. This is forward reaction. This is the reverse reaction, right? So if I gave you this graph right here, and I asked you at what time did this reaction reach equilibrium, what would you tell me? Estimating, roughly
About 50.
about 50, right? If we drop the dotted line down here, right, it would be roughly 50 when we reach equilibrium. Equilibrium at 50 seconds. I don't know why I wrote S in parentheses. I was just thinking, is it seconds or milliseconds? But what's seconds? Okay. So 50 seconds it reached equilibrium. All right? But let's say, I need to make myself some more room, so I'm just going to write EQ there for that. Let's say at 80 seconds, we dump some more N2, some more nitrogen gas into the reaction. All right? So at 80 seconds, we added more N2. And so what's going to happen? Well, all of a sudden now, the reaction rate on this side, because we've got more reactant over here, is going to jump up again, right? And basically the reaction is going to have to work towards equilibrium again, all right? So it's going to do this number here, and we're going to reach our second equilibrium at the way it's drawn here at 100 seconds. Does everybody see that? So this is the new EQ right here. So at this point right here, we added more N2. So immediately when we did that, the forward reaction increased, right? The forward reaction jumped up, and it started slowly making some more products, so they started catching up, and then we reached a new equilibrium. Does that make sense to everybody? The way that graph, the way you read that graph? Well, this is what Le Chatelier says about that process. Le Chatelier's principle basically says when an equilibrium is stressed, and in this case it was stressed in that we added more reactant to it, it will shift in a way to relieve that stress. And reach a new equilibrium. So it's always shooting for this equilibrium, all right? So what happened with this reaction, I'll let you guys finish writing that down. So with this reaction here, we added N2, and so we got a lot, the concentration of N2 got much greater on this side. Does that make sense? Right? But what's going to happen with the reaction is since we added N2 over here, it's going to shift towards the products. It's going to start making more product because it's trying to get back to equilibrium. The concentrations are out of balance, right? It's really high here, so it's going to shift away from this. Since we added more reactant, it's going to shift away and make more product, all right? And so that's why you see this part of the curve here increasing up, because it's making more product to reach that other equilibrium. So the way that we would write that, when you change the concentration of something, is this is what goes along with this Le Chatelier's principle. An equilibrium will shift away from the side that experiences an increase in concentration. Or another way to say that, or will shift towards the side that experiences a decrease in concentration. All right. So in our case here, the increase happened on this side, so we would say when the event curve occurs where the red starts, reaction shifts towards the products. Because we got an increase in concentration on the reactant side, so it's going to shift to the other side of the equation. Does that make sense to you guys? Well, let's see if it does. All right. It's a really simple process, and you're basically going to have some equations on the test that are like this next question here. You need to be able to figure out what's going to happen as we adjust certain things in our reaction. All right. So let's say that we have this 4 Cu plus aqueous plus S as a solid plus 3 H2O as a liquid, and this is an equilibrium reaction. I'm just going to write my products down below here because I'm running out of room. 4CuS plus H2O SO3 aqueous plus 4H plus aqueous. So here's the question that they ask us. What will happen to the concentration of H plus? So this right here, what's going to happen to the concentration of this guy, H plus? What's going to happen to that if the concentration of Cu plus goes up? In other words, Cu plus is added. So if this concentration goes up, what's going to happen to the concentration of H plus? Which way is the reaction going to shift? We added more what? We added more product or reactant? We added more reactant, right? So it shifts away from it. It's going to shift towards the product, which means it's going to make more of this stuff. Does that make sense to you guys? If this goes up, it shifts away from this to make more stuff on the product side. So the concentration of H plus will go up. All right? Questions about that? What if instead of that happening, so let's do this exercise again. We're focusing in on H plus. We want to know what's going to happen to H plus if the concentration of this stuff here, H2SO3, if some of that's removed. If some of H2SO3 is removed, what does that mean happens to the concentration of H2SO3? Is it going to go up or down if we remove some of this stuff? Up. Because we removed this? I'm just saying, I'm not talking about how it shifted yet. I'm just saying if you've got a certain amount of this stuff in the reaction and we remove some of it from it, do you see that overall we have less of that, so the concentration of that stuff goes down? Okay, so the concentration of this guy is going to increase. Now decrease. So how is the decrease in this concentration going to affect this concentration here?
Down as well.
It doesn't, because remember, if you have a decrease, it's going to shift towards the side where the decrease occurred. All right? Right? So if the product side decreased, then it's actually going to shift in this direction to compensate for that, and this is going to go up again. Does that make sense? All right? We increased the concentration of a reactant, it shifted towards the product, which means this went up. We decreased the concentration of a product, and it shifted towards the products, right? Because it shifts towards the side that experiences a decrease in concentration. So the product concentration went down, so it's going to shift towards the product side, and it's going to make more of this stuff. All right? So in this case, H plus increases as well. When I said that the second time, did it make sense the second time, Evan? Because you said
actually made less sense because it says that equilibrium will shift away from the side that experiences increase.
Right. Which side experienced the increase? The reactant side experienced a decrease, which means that the increase happened on the product side. I had this down until you mixed it up a second ago. Now I'm totally off.
Sorry.
The product side experienced a decrease, which meant that the reactant side got increased in concentration. So it shifted away from that and went to the product side. But it may be easier in this case when you're thinking about decreases, just think this. If it decreases, it's going to shift towards the decrease. If it increases, it's going to shift away. Okay?
It increases, it shifts away.
Right. So the first time it increased on the reactant side, so it shifted away from that to the product. The second time it decreased on the product side, so it shifts towards where the decrease was.
Oh, gotcha.
Does that make sense?
Because it decreased, it increased the part that had already decreased. Is that right?
Because it decreased, it shifts towards the decrease. That's the simple way to think about it. It decreased on the product side, so it has to shift towards the products. All right? Had it increased on the product side, it would have had to shift away from the products to the reactants. All right? So it shifts away from where the increase is, it shifts towards where the decrease is. That's really all you have to remember. All right? What about if more S is added? What if we add some more of this stuff here? What's going to happen to the concentration of H plus?
Goes up.
If we add more S, what's going to happen to the concentration of H plus? Nothing, because S is a solid. Right? You don't include solids and liquids when you're dealing with equilibriums. So you ignore the S. So you would also have to ignore this guy.
And the H2O, right?
And the H2O, that's right. Yep. So these are it's only the concentration of these things that will affect the concentration of the others. All right. So let's think about this one more time. Let's ask it from this perspective. I increase the concentration of H plus. what happens to H2SO3? Does that concentration go up or down? It goes down, because I increased on the product side, so it shifted towards the reactant side, right? So everything over here goes down, right? Let's say I decrease the concentration of H+. What happens to the concentration of Cu+? I decreased this. What happens to the concentration of this? I decrease this. Which way did it shift towards if I decrease this? It has to shift towards the product, so this goes down since it's a reactant. Does that make sense? Yeah? So it may be helpful in your mind whenever you say the easy thing to do may simply to do concentration of this went down, then it's shifting this way. So everything on the reactant side goes down, everything on the product side goes up, right? If the concentration on the product side goes up, it shifts that way. So everything on the reactant side goes up, everything on the product side goes down. All right, so it may be helpful whenever you see that to put an arrow so that you can kind of figure out which way it's shifting. Okay? And ignore solids and liquids. Don't forget that. All right. Just two more things to note, all right, that they tell us. We'll also, it's just kind of the same idea with the, it's really the Chaney's principle, but it's as it connects with temperature and temperature and pressure. All right. If we have a reaction like this reaction here, PCl3 as a gas. And it's an equilibrium reaction, and whoops, there should have a plus there, plus CO2 as a gas, and then PCl5 as a gas. All right, so they give us a reaction like this, and they tell us that for this reaction here, that it has a change in H of negative 92.5 kilojoules. Now, we didn't get to study change in H, right? Does change in H mean anything to you guys? All right. Change in H is change in energy. So we have talked about the heat stuff, right? And so it's just talking about heat as a form of energy. And so we're talking about when energy changes. And the way it works is that if change in H, which is a change in energy, if change in H is negative, reaction is exothermic. What does it mean to be exothermic? Gives off heat or absorbs heat? It gives off heat, right? Gives off heat. Gives off energy. Heat is energy, so we'll say gives off energy, all right? If change in H is positive, reaction is endothermic. All right, so absorbs energy. So there's two ways to think about it. You can think about this when it's exothermic, it gives off energy, or energy is a product. Okay? If it gives off energy, the energy is over here on this side, right? When the reaction takes place. If change in H is positive, the reaction is endothermic and it absorbs energy, or energy is a reactant. Okay? So for this particular problem, they tell us that change in H is negative 92.5 kilojoules. Change in H equals negative 92.5 kilojoules. That's the energy. Right? We're familiar with joules. We used that in chapter 13. That's the energy that this guy, that's a part of this reaction. Is this reaction endothermic or exothermic? Exothermic, because it's negative, so we need to think of energy as a reactant or a product? A product, all right? So what we're going to do is we're going to write this 92.5 kilojoules over here, okay? And so if we think about it like this, then the way that temperature affects this, we're gonna think about it exactly the same way that we think about where we use Le Chatelier's principle over here. And this is what it says. It says when temp is increased, equilibrium shifts away from side containing energy. Okay? If temp lowered, the opposite happens. Shifts towards side with energy. Right? So the question for this example here is what happens to the concentration of PCl5? All right, we want to know what happens to this concentration here if the temperature is increased. Now, per this principle here, which way is it going to shift if we increase the temperature? Right? Think of it as the concentration of the temperature of this energy, right? The concentration of this energy goes up, and Le Chatelier's principle says, well, it's got to shift away from it since it went up. Okay? So temp increased, it shifts away from the side that contained the energy. So what's going to happen to the concentration of PCl5? If the reaction shifts this way, it's going to go down, right? It's shifted towards the reactants. It's a product. So it goes down. Does that make sense? It's the exact same thing that we just did whenever we add more of something to the reaction. What did we add more of? We added more, when we raised the temperature, we added more energy. So it's like the concentration of this guy going up, right? And so if the concentration of the energy goes up, it shifts away from that, per Le Chatelier's principle. And so the concentration of this goes down, the concentration of both of these guys are going to go up, right? If we lowered the temperature, that would be like decreasing the concentration of this guy. And what's the reaction going to do if we lower the temperature? It's going to shift towards the products, right? So this goes up, and these two guys would go down. Does that make sense? Right? It's the same exact concept. It's just they're telling you how temperature figures into it. All right? Last thing with the Le Chatelier's principle, and it's the same exact concept one more time, but this time it's related to pressure. And it says this. It says when pressure goes up, equilibrium shifts away from side with more gas molecules. If pressure goes down, shifts towards side with more gas molecules. If no gas molecules, pressure doesn't affect it. All right? here's the easiest way to think about this. It's the same thing that we've done like we did here with heat, all right? Instead of adding heat, instead of adding energy on here, all right? Which side of this equation has the most gas molecules?
Reactants.
The reactant does, okay? So I want you to think of pressure as being added to this side. It's on the side with the most gas molecules. Because gases are very much affected by pressure, and if there's more gases, then this side's more affected by pressure than this side is, okay? So that being the case, if we're told that the pressure goes up, in other words, this pressure concentration increased, right? Let me make sure that everybody knows this is pressure and not, what is it, phosphorus or whatever capital P is, right? If the concentration of pressure increases, what's going to happen to the concentration of Cl2?
Go down.
It goes down, right? Because this side increased, so it went that way. So this side goes down. The concentration of this side is going to go up. Make sense? It's Lesagnier's principle again, but just with pressure. If you understand that pressure needs to be on the side that has the most gas molecules. Okay? And what do I mean by most gas molecules? I mean, like if there had been numbers in front of this, let's say this had been 1 and 1, but this had been a 3. This has more gas molecules because this only has 1 gas molecule and another gas molecule, which is 2, and this one has a total of 3. Okay? If it had been this, now we've got the same number of gas molecules on each side, and the pressure doesn't affect it. Because we don't have more gas molecules on one side than the other. Okay? You guys think you could do that? You totally can. I have complete confidence in you guys. You're going to rock it. Alright? The good news is I recorded all this, so you can go back and watch it if you need to. And you're going to have some homework problems that will help you, give you an opportunity to practice this. And this is what our last test is over. I will just tell you guys, the last test is always really, really fast because it's so easy. I mean, because this is all it is, right? It's basically calculating K and then figuring out which way the concentrations are going to shift based on adding more or taking away, adding more of a substance or taking away, increasing or decreasing the temperature or increasing, decreasing the pressure. So it goes pretty fast. So what that means is that I can still answer a few questions at the beginning of class next week if you're confused about any of the program, the homework problems before you take the test. Okay? Cool? Yes?
At the end of the semester, you're still going to drop a quiz grade, right?
I am, yes. All right? Yep.
Should Emma's name be on anything?
Oh, I'm sure it should. Where's my... Here.